Don't brag. So what do we got here? So remind me, what were our special limits from yesterday? We got two special limits. We want to write those down because we're gonna rely on those.
Sine of x over x.
Okay, so the limit of sine, I'm gonna call it theta, over theta as theta does what?
Approaches 0.
Good. Approaches 0 equals 1. So there's an indeterminate form that we've resolved. Instead of being 0 over 0, the answer is 1. I haven't proved it to you yet. And like I say, that might be after the AP test, but we'll just take it on faith for now. Another one too. Another limit. The limit of what? Remember, this was the weird
Oh,
one.
I got
It
it.
involved cosine.
1 minus cosine x.
Call it theta.
Okay, over theta.
As
Theta approaches 0.
equals
0.
0. Okay? So those are the two we have. All right, so we've got to, for a problem like this, we've got to somehow get one or the other of those to show up, right? So we've just got to use our trig identities, trig definitions, etc. So let's work through this together. So what do we think here? It's the first thing I probably want to do. Okay, so we're going to write the composite trig functions in terms of the base trig function, sine and cosine. So secant is 1 over cosine theta. Okay, now what? What do you think? Just throw out some suggestions. Okay, look, good. So it looks like we got some complex fractions going on there, right? We got fractions of fractions. So what's that? That kind of triggers something when we see complex fractions. Good. We want to simplify top, simplify bottom, right? So on the top, we get a common denominator, which is going to just be cosine theta. Okay, so that's going to give us, if that's going to, I'm going to have to multiply it by cosine theta over cosine theta here. Oh, what do you know? Yeah, so we're going to get 1 minus cosine theta over the common denominator, cosine theta on the top. Everybody agree? Okay. On the bottom, we've just got theta over 1, right? So we got it. So we got fraction on the top, fraction on the bottom. What do we do with the bottom one? Flip and multiply. So that's going to leave us with the quantity 1 minus cosine theta over cosine theta times 1 over theta, right? Okay, and so I want to kind of reorganize this a little bit, don't I?
Yeah.
What's going to go with what? There, so how about that? And that will group together. So we'll just commute the two factors on the bottom, which we can do, right? So this is going to look like the limit of 1 minus cosine theta over theta times what's left over, 1 over cosine theta, okay, as theta approaches 0. Now, technically, we want to break those into separate limits, but we don't need to, right? That's just kind of a waste of time. We could. I mean, if we're going to strictly follow the rules, we'd have to break this up. We skip this step, though. We'd have to break this up into limit of 1 minus cosine theta over theta, as theta approaches 0 times the limit of 1 over cosine theta as theta approaches 0. But we see that up here, don't we? Right? We can see that this one's going there and that one's going there. And we can just get answers out of this. So what's this equal to? This is our red limit from up here, isn't it? Oops, incorrect. Right? That's our indeterminate form. And so we're just going to get, this is equal to 0 times, what's this one going to be? If I evaluate that directly, what's the limit of 1 over cosine theta as theta goes to 0? What's cosine of 0? 1. So I get 0 times 1 equals, that's our answer. Yeah. Right?
Yeah.
But remember though, the whole point here was, we had this indeterminacy. If I tried to evaluate this thing directly, I got 1 minus 1 over 0, which was 0 over 0. Right? Which means more work. The way we resolve it with our trig limits is we had to be able to rewrite this in a form. So the only way we're going to get rid of that indeterminacy is to have factors that include, one of those indeterminate forms of special limits, trig limits. Okay. All right. Kirk had another question. This guy. Okay, this one came from this is like the second assignment, right? Over the analytical stuff. So this was the one where the practice where we're dealing with radicals and complex fractions, right? So this is a radical one. As x approaches 64, we're getting 0 over 0, aren't we? So this is indeterminate. So what does Kirk did some kind of shenanigans on this one, but he wants to know how are we going to get this, like, using the pattern we used before, right, without having to do anything strange. So let's just follow the rules on this one and see what we get. So when we have, now think why this rule applies. When we have an indeterminate form where we're getting a 0 from an expression that involves a radical, right? So in other words, this is the red flag for us, isn't it? Yeah. 8 minus the square root of x as x approaches 64 is giving us a 0. And that's part of the indeterminacy, right? So we started off with 0 over 0, which is more work, right? Okay, so what's our more work look like? Okay, good. We'll multiply by 1, but we'll multiply both the top and the bottom by the conjugate of the top, right? So we'll multiply through by 8 plus radical x over 8 plus radical x. And so that's going to give us, on the top, what? 64 minus x. On the bottom, it's going to give us x minus 64 times 8 plus square root of x. Right? Okay, so we still get 0 over 0. But what's that equal to? What's 64 minus x over x minus 64?
-1.
-1, right? So that part right there just goes to -1. And the reason being, you don't even have to necessarily show this, but the reason being that the top we can break up into negative x minus 64 and cancel the x minus 64s, right? Right. So we're going to get a limit of -1 over 8 plus the square root of x as x approaches 64. Now we can directly evaluate, right? plug in our 64 and we get negative 1 over 8 plus 8. Okay, make sense? Okay, all right. So, new stuff. Let's take a quick look at one slight difference. Not a big deal at all. This is really minor stuff. It doesn't give you any hard problems to do or anything. It's just kind of a new definition. So one-sided limits. Sometimes indicating the limit of a function fails to exist. Sometimes a function has a limit that fails to exist because I'm just going to word this differently. You can read this stuff later if you want. But we talked about this earlier. This is one of the types of places where a limit fails to exist. Right? We said that the ant is approaching different values from different directions in this case, or there's a gap in the function, right? So previously, if we answered the question, what is the limit of call this g of x, I guess. The limit of g of x as x approaches 2, we would have just said does not exist. Right? Okay, that's true. It doesn't exist. But we can be more specific than that. Right? We could be more specific in describing the direction in which we're approaching the limit, from which we're approaching 2. Right? The value where the limit doesn't exist. So what if we were approaching from the left? What would the limit be? Think about an ant approaching a value of x equals 2 from the left. What y value does he anticipate stepping on? Negative 1. Okay. How about an ant approaching x equals 2 from the right? 1. That makes sense, doesn't it? Right? Even though, yeah, our limit, as we described it earlier, fails to exist because one criterion that we established was that ants approaching from opposite directions had to agree, right? And they don't agree here. And so which would be the preferred answer? There couldn't be a preferred answer, and so we get none, right? But we could do this a little differently. We could use what's called a one-sided limit, and we could describe it like this. We could say that the limit of the function g of x that I just graphed as x approaches 2, now what do you suppose this minus sign means right there? It's like a superscript. It looks like an exponent, but it's just a sign from the negative direction. So that would be from the left, right? On the real line, the left is to the negative directions to the left, positive directions to the right. So if we're approaching the value of 2 from the direction of negative infinity, right, then the answer that we get is negative 1, right? And that's what we saw on our graph. So that's the notation we use for a one-sided limit. We just attach this negative or positive superscript to tell us where we're coming from. So that always means, when you see that, that means a one-sided limit, okay? Because you're only approaching from one direction. Okay, well, obviously then if we want to approach from the right, instead of a negative, we're just going to get a positive, right? And that answer was positive 1. Okay? So that's a one-sided limit. Let's look at a couple examples. So, I guess quickly, let's take a look at this. So this is off the OpenStax thing. I'll show you where this is in your book too, but it's confused with another topic in your book that I don't want to talk about today, with continuity. Now we're not going to talk about that until after round 1. And so it kind of gets mixed in with the whole idea of continuity, and so that's why I just used this textbook for today. Later on, we can come back to the other book, and it'll say the same thing, but slightly different context. So how do we define these? What's our informal definition? Well, this makes sense. We would read this as the limit of f of x as x approaches a from the left is equal to L. That makes sense if this is true. If f of x is defined as some function, it's defined in all intervals that include the point surrounding the value x equals a, but possibly not even including x equals a, right? So in other words, on our graph, we've got to be able to say that we're approaching, like we're approaching from the left, that the function is defined in this region that up to, but maybe not including 2 in this case, right? We couldn't have a bunch of holes in there where they're right next to that point. That screws things up. Down here, we don't care what happens. But the ant has to be able to take some steps towards this hole in order to be able to say, okay, I anticipate stepping here. Does that make sense? Like if this were just some discretely defined function where there were just a series of points, that wouldn't make sense at all, because the ant wouldn't be able to ever see a pattern developing, right? So it's got to be defined on an open interval up to, maybe not including 2 though, right? If that's true, then if this statement is true, if the values of the function f of x approach the real number L as x approaches a from the left, then this is true, right? This is true. If in other words, the closer the ant gets to x equals a from the left, the closer the function gets to some single value L, then that's a one-sided limit. Okay, same thing would be true from the right. If the function is defined on some interval that's to the right of x equals a, possibly not even including x equals a, so the ant could walk backwards and establish a trend, right? Could walk backwards and say, okay, I anticipate stepping on a certain value, even if the function doesn't exist there, then we're fine, right? So as the ant approaches a from the right, the closer he gets to a, the closer he gets to the y value of L, then we'd say that the one-sided limit from the right occurs. All right? So that's a limit from the right and a limit from the left. Okay, now think about this. Any questions on that so far? I mean, it's just pretty, I'm sort of glossing over it a little bit because it's probably that simple to think about. It's exactly the stuff we talked about previously. I want you to make a connection here, though. One of the things we said about limits before, right, was that in order for the limit to make sense, to exist, the ant had to be able to approach from both sides and anticipate stepping on the same place. So how could you connect our definition of a regular limit, which we might call a two-sided limit now, to the separate one-sided limits? How could you maybe rewrite that definition in a little better way? A regular two-sided limit exists if what? What would have to be true?
If approaching both sides is the same value.
Okay, so if the limit of f of x as x approaches a from the left exists, and the limit of f of x as x approaches a from the right exists, so they both exist, and they're equal, then you'd say that the two-sided limit occurs, right? See, that's just a little tighter, more technical definition than what we had before. So we could just say something like that, right? There, that might be our new and improved definition of a limit. If f of x is a function defined on all values in an open interval containing a, with the possible exception of a, right? Every place around a, but maybe not including a, and let L be a real number, then if the limit of f of x as x approaches a from the left equals L, and the limit of f of x as x approaches a from the right equals L, then the limit of f of x as x approaches a equals L. The two-sided limit exists, right? So if and only if, this kind of goes back to earlier stuff, that's a double-sided arrow. Remember what that means? Just kind of a mathematical nicety here. I want to make sure you understand. When you have an if and only if statement in math, like if I say something like A, if and only if B, that stands for if and only if, IFF. What's that mean?
Equation's reversible.
So it's reversible. So it means it's a biconditional statement. It means if A, then B, and if B, then A. Those both have to be true. Okay? So we can read this both ways. In other words, we can say that if we know that the two-sided limit exists, then we know for sure that both of the one-sided limits exist and equal the same thing, right? Or we can flip it around and say if each of the one-sided limits exists and they agree, then the two-sided limit exists. Okay, just kind of some terminology stuff. So let's look at a couple quick examples. How about something like this, a piecewise function? I want to show you, we'll start talking about piecewise functions just a little bit. So does this all make sense to everybody, this piecewise function? Stare at that for a second. And I want you guys to collectively kind of explain what that means. So whenever I see something like this, whenever you see something like this, that's a piecewise function, right? That tells you that a piecewise function is coming. The function is defined in different pieces, right? So what does this top piece mean? Maisie, what's that mean?
That if x is less than 2, then y is.
Okay, good. So on this piece of the function, when the domain includes all values of x less than 2, then the behavior of the function is that it's y equals x plus 1, or f of x equals x plus 1. Okay? When x is greater than or equal to 2, we only, then this is the part of the function that exists, right? They don't overlap, obviously. If this is a function, and this is a function, right? It tells us it's a function. Remember what that tells us about, like, for example, the vertical line test. What's the vertical line test mean? The test for, to see if a relation is a function. It's a function if what? If I slide a vertical line across the graph, what has to be true? Okay, it only intersects once, which means that the graph cannot overlap vertically, right? Which fits our basic definition of a function. For each input, there's only one output value. For every x value, there can only be one y value. So notice that these don't overlap. They transition at 2. That's a boundary between the two pieces, right? So we could graph this thing. I'll show you how to do it. Kind of nice to know. So on the graphing calculators, here's how you do it. Oops. There we go. So if I want to graph this piecewise function, here's how you can do it. So you go to the y equals menu, and then you go second math. Oh, hang on. No, not second math. I go math. And then, yeah, and it's easier to scoot up from the bottom to piecewise. That's a new feature on the new operating system. Does everybody see that on your calculator? Doesn't show up on your calculator?
No.
Really?
No, we just have summation, sigma, log this, and result.
Really? Let's see something here.
Yeah, our calculator probably needs to be updated. Yeah.
What's your operating system? Go to second memory. What is it?
0.1.
Okay.
Where's the operating system on second memory?
Right there. Should say right up there.
I pulled up the second memory, and then it's got about, memory management.
About.
Okay.
Okay, what if it's not a CE? What does it show up as?
Well,
5.0.1.0012.
Okay. Okay, so let's try this. I want you to get you the new, so this is kind of important to do. Let me see if this works, first of all. You know what, I'm not gonna do this now. Well, I'll do this tomorrow. Well, you guys are, something you're gonna be watching, I'll try to do this while you're watching
we're
it.
gonna watch something.
Yeah. Okay, so here's how it'll work on yours then. Yours won't have that. Yours will be a little different. It's not gonna work on mine, but this will work on yours, I think. So for now, open up a set of parentheses, and then you're gonna put the function, so it'll be x plus 1 in parentheses, okay? And then open up another set of parentheses, so it almost looks like a product, but it's not. And inside the second set of parentheses, you're going to put the domain, okay? So we'll do x is less than 2. So you go x, now where's less than? That's in the test menu, so it's behind math. So you go second, math, and it'd be number 5, right? Okay, x is less than 2. And if you close that set of parentheses and you go zoom 6, yours doesn't look like mine then, correct? Yours, why is mine doing that? Hang on a second. Oh, why did it do that? Okay, mine's messed up because I have the new operating system, but does yours do what it's supposed to do? It looks just like this, but it shouldn't have this other line right there.
It does.
It does?
Yeah, mine does too.
Really? Okay. I don't know. Then this is where I'm kind of in limbo, because that's the way it used to work, but evidently there was some other way in between. So let's not mess with this, because we'll get the new operating system anyway. So, never mind. But the thing is, we don't even need the graph anyway, so let's not bother with it. We don't want to use the graph. We want to do this analytically. Okay, so let's do both of these. Let's do both of these, using algebra and calculus instead of using graphs and tables and things, right? So if we do part A, the limit of f of x as x approaches 2 from the left is equal to the limit of what? And y? If I'm taking the limit, here's my piecewise defined function, right? If I'm taking the limit of this function, f of x, as x approaches 2 from the left, right? That's not negative 2, that's 2 from the left. What am I going to get? Okay, but tell me this first of all. What am I going to plug in for f of x? Okay. Everybody see that? That's going to be the green part of the function. Because look at the domain. When we're approaching 2 from the left, would everybody agree that we're on the green domain? Okay, so we have to evaluate the green function. So what's our answer going to be then? Yeah, right? Because we're just going to plug in 2. Does it matter that it's 2 minus? No. What's the number we're approaching? 2. The minus only indicates a direction, right? The value is still 2. So we're just going to get 2 plus 1 equals 3. Okay? Say it again.
When do we put the negative?
When you put the negative in, you mean up here? I mean, we could, but what does that 2 negative mean? That just means a value approaching 2 from the left, so like 1.999 infinity, right?
Yeah, I don't really know.
Well, I think you're,
No, I confuse myself.
okay, if you think of something
Okay.
fast. So part B, the limit of f of x as x approaches 2 from the right is going to be the limit of what function? What color? Purple, right? Because we're on the purple domain. As x approaches 2 from the right, we're talking about values like 2.0001. Well, that's on the purple domain, right? So we're going to get the limit of x squared minus 4 as x approaches 2. And what's that going to give us?
0.
Yeah, I'm going to get 2 squared minus 4, which is 0. So if we graphed it, that's what we find. There's a break in the function there. Okay? They don't meet. Okay. How
What
about,
would your answer be? 2.
so say it again.
What would your answer be?
So that there's the answer to part A, there's the answer to part B. Right? Because all we're saying, think what we're asking. In terms of ands, This is saying, what value does the ant anticipate stepping on as he approaches an x value of -2 from the left? He would anticipate stepping on a y value of 3. Another ant approaching from the opposite direction, approaching 2 from the right, would anticipate stepping on 0 if we graphed it. Okay.
So let's write that out here.
No,
It's
those would be the answers.
But they'll probably be two separate ones.
Like, he's like,
Mhm.
should we put a comma in between them? Like, he's asking that. If
On
they
Moodle,
were on-
yeah.
It was on Moodle.
Oh, on Moodle? Oh,
Moodle
yeah.
is
I mean, it'll be obvious with the question. I think it'll be like separate your answers with comma or something like that, yeah. I got you. Okay, so what about something like that? Okay. So we're gonna skip the part where we do a table of values, just because I don't want to do it. You could though, right? Is everybody okay with how to do that?
Yes.
How to do the tables? Anybody want to see a quick example of making the tables?
Can I ask a different question?
Yes.
Kind of the same question. but-
Okay.
So what happens if they just ask you to find the limit for that and don't tell you there's one side, so you don't have two? Can you just write both of them out?
Okay, so if it says, does the limit, I got you. So the same question on the last page, but it just wanted to know what's the limit of f of x as x approaches 2? The answer would be, doesn't exist.
So just, okay.
Right, right. Only if you're, if you're specifically asking about one-sided limits, then that's different.
Okay.
Okay. If they wanted to, like, let's say this were on, I'm not gonna say it, I'll say it later, because where this will make more sense, when we talk about continuity, that's when we'll come back and look at this and we'll be able to talk about it in more detail and say more about it. So for now, I'm just gonna leave it at that, okay? Okay, what about this guy? We're not gonna do this using tables for now. If we need to see another example of that, we'll come back, but I wanna look at one more thing today. How could we do this problem without using tables or graphs? Okay. Okay, and it's what's the difficult part of this problem? What's making it weird? The absolute value. Okay, so we got to talk about absolute value functions for a second. So let's focus on the absolute value part. If we have the function x squared minus 4 inside absolute value bars, we got to remember what the definition of an absolute value function really is. So the absolute value of a, we always want to write absolute value functions as piecewise functions, and then we can do algebra and calculus on them, okay? So the absolute value of a is equal to, and you might want to put this in your notes. So the absolute value of a, we can break it up into 3 parts. When a is greater than 0, so whatever's inside the absolute value bars is greater than 0, then we get the function just equals a. Okay? Whenever what's inside the absolute value bars is negative, what does the absolute value do to it? Makes it positive. Well, how do you make a negative thing positive? You multiply by -1, so it'd be negative a, right? And then in the middle, when a is equal to 0, the absolute value of 0 would just be 0. Okay? So how does that apply here? Well, for this problem, this is going to equal, when x squared minus 4 is positive, it's not going to change anything, right? So it's just going to equal plain old x squared minus 4 whenever x squared minus 4 is greater than 0. Okay? Whenever x squared minus 4 is less than 0, it's going to be the opposite of x squared minus 4. And in the middle, when x squared minus 4 is equal to 0, it'll equal 0. Okay? But that still is not where we want to be. We'd much rather have this written as an inequality or a compound inequality in terms of x. Because we want to be able to know as I graph this thing, where on the, on the xy plane, for what values of x am I going to graph this function, and for what values of x am I going to graph this function, right? Let me pause there, though, and make sure everybody's okay with this statement. How much time we got, by the way? Okay. Everybody okay with that? The absolute value of hand is equal to hand whenever hand is positive, right? The absolute value of hand is negative hand whenever hand is negative. And the absolute value of hand is equal to 0 whenever hand equals 0. Okay, but let's focus on this part right here, for example. So everything in the green bubble, what does that mean? Where is x squared minus 4 greater than 0? How are we going to deal with that? This would have been something probably from last year, but we'll review it. This is a pre-calculus issue. How do we deal with something like that?
You solve for over.
So we want to do, when is x squared minus 4 greater than 0?
That's great.
When x squared is greater than 4 is one way to look at it. Okay, so here's another way to think. There's several ways we can think about this algebraically. One way would be just try to isolate x. So if x squared is greater than 4, then the problem is you can't really square root both sides of this. Because if I square root both sides, that would be like saying that's when x is greater than 2, but that's not the complete answer, right? Think what happens if I square root this. If I square root both sides, well, what is the square root of x squared equal to? That's the absolute value of x. That's the definition, that's the algebraic definition of an absolute value function, not the piecewise function definition, right? Doesn't that make sense? The absolute value of x equals the square root of x squared. Try it on for size and see if it works. Let's try, it's evaluated at 3. So that would say that the absolute value, of 3 equals the square root of 3 squared, which is 3. That works, right? How about the absolute value of negative 3? That would mean that the square root of negative 3 squared, well, what's that equal to? 3. It works, right? Okay, so if we're going to go this route, then that means that what we've said is the absolute value of x has to be greater than 2. Okay, well, what does that imply? If the absolute value of x is greater than 2, this goes back to algebra 2, right? If you have a absolute value inequality, what do we do with that? Got to split it into 2 parts, right? We know that if the absolute value of x is greater than 2, then that means that either x is going to be greater than positive 2 or x is going to be less than negative 2. Right? Okay, so there's our domain for the first part. Okay, so we can replace that with x is x is less than negative 2 or x is greater than positive 2. Okay, what about down here? What do you think is going to happen there if we do the same thing? If we did all the same algebra, right? So let's just kind of do this algebra right here. So we had x squared minus 4 is greater than 0. Well, we could have added 4 to both sides. Less than. Whoops. So x squared is less than 4. I could square root both sides. We get the absolute value of x is less than 2. Well, how do we transition between an absolute value inequality and a compound inequality? If it's a less than, then remember that means that x is going to be trapped between negative 2 and positive 2. Okay, so there's our domain for the other part. X is greater than negative 2 and less than positive 2. Okay? And in the middle, when is x squared minus 4 equal to 0? When x equals 2. Okay? Now let me show you a different way to do that, though. Okay, I'm going to show you another way to do that. Question? Negative 2 also. Yep. Equals plus, you're right. Plus or minus 2, I'll put. Right, because if we solve that, we get 2 answers with plus or minus 2. Okay? So here's another way to do this one. We can do the same thing. Actually, I want to borrow that piecewise function. Let me borrow, I'm going to borrow this part right here.
And then we're down to 2 minutes.
2 minutes. Well, we may not finish the whole thing.
Okay.
So if not, we'll pick this up later. You know, a lot of what calculus does that's really cool about calculus is it brings together all this other stuff you've already done. And you just kind of, all of a sudden, it all comes together and it just makes sense. Maybe not immediately, but it does eventually, I promise you. Okay, so what about this? If we want to do the same thing, if we want to say something like this statement, when x squared minus 4 is greater than 0, here's another way to do this. Okay, another kind of cool way to do this. What if I factor x squared minus 4? Okay? That factors into x plus 2 and x minus 2, right? So we know, now think about this, at 1 minute. Yeah, I give up. We'll take this up in 1 minute.